This is Hyunsu Kim from KAIST. In this talk, I'm going to present about learning probabilistic models for static analysis alarms. This is a joint work with Mukund Raghoswaman from University of Southern California and my advisor, Kyung-ha. Static analysis is a technique that understands given program without actually executing it. We can use the technique to find bugs in a program. The user would get an alarm report that indicates program points which are likely to be bugs. In static analysis, one of the big challenges is false alarm. The alarm report typically contains both false and true alarms with no order of significance. A developer has to go over the alarms one by one without any guidance. This eventually harms the usability of static analysis in the real-world deployment. To tackle the issue, alarm ranking system was introduced. The system initially gives a ranking of the alarms sorted by the likelihood of being a bug. From the ranking, now a developer is provided with the priority of an alarm inspection. The developer inspects the alarm from the high-ranked ones and gives a feedback to the system. The feedback is whether the inspected alarm was true or not. In other words, a bug or not. Then, the system integrates the feedback to provide better alarm rankings to the user. The computation basically follows the Bayes rule, that is updating the belief with the new information. Here, the belief is a likelihood of an alarm being a bug. Ideally, the system should push the true alarms ranking upward within less user interactions. Here's a result with wget, the well-known GNU utility. With sound interval analysis to detect buffer overflows, we get hundreds of alarms while only 6 of them are bug. Here, the code size is about 65,000. You may imagine how inefficient it is to go over the entire alarms for a few bugs. The graph shows the performance of the interactive alarm ranking system. X-axis denotes the number of user interactions, and Y-axis denotes the sum of rankings of true alarms. The faster the ranking drops to 1, the better the system is. Orange dashed line shows the performance of the system requiring less than 200 rounds of interactions until finding all the bugs. One can argue that the number is still overwhelming. However, considering the number of alarms is nearly 1,000, it effectively reduces the inspection burden by 80%. But still, as marked with black arrows, the system shows awkward moments where the true alarm ranking suddenly spikes. If we could resolve the moments, we would significantly enhance the performance. That being said, the blue line denotes the performance of our suggested learning framework. The learned model reduces the alarm inspection burden by about half amount additional to the original system. To get into the details, we explain how the Bayesian alarm ranking system for a given program is constructed. Again, the example program is GNU wget. You don't have to understand every bit of the program, but notice that the true alarm is tightly coupled with false alarms. We first proceed with the approximated interval analysis. The analysis not only reveals the buffer overflows, but also keeps track of the data flow. The atomic data flow is denoted as an edge. For example, edge 4,5 means there's a data flow from line number 4 to 5 with variable line. From an edge, we can trivially derive a path. Then, we also observe another edge 5,6 with variable talk. Now, by taking two facts into account, we derive a new fact, path 4,6. This means there is a data flow from line number 4 to 6. Notice that the new fact elongates the known data flow, path 4, 5, with an edge. By inductively applying derivation mechanism, we eventually observe the data flow to the alarm. If we do it for all the alarms, we construct the derivation graph as shown on the right. One can see that false alarm at line number 8 is closely related to the true alarm at line number 11. We can formally describe the derivation process as a simple logic program. Each line denotes the logical rule, saying when the right-hand side is true, the left-hand side is derived. For example, the last rule denotes that if there is a path from x to y, and the overflow is observed in y, then alarm at y is derived. Here, the derived fact about each alarm is binary, either true or false. And this is a logical representation of alarms. With logical reasoning, we can only derive if the alarm is either true or false. In order to make probabilistic reasoning possible, we use the Bayesian network framework. In the framework, the logical rule now turns into a conditional probability ranging from 0 to 1. For example, consider deriving an alarm from known path and overflow. The conditional probability now represents that if both path and overflow is true, then the alarm is likely to be true with probability 0.99. Note that the probability itself is a trainable hyperparameter. And to meet the reality, if any of the facts in the hypothesis is false, the conditional probability is 0. Then we impose such structure to enable probabilistic inference over the alarms. We assign a probability to basic facts and the derivation rule. We can compute the probability of alarms through chained application of Bayes' rule. The probability of an alarm is then used as the likelihood of being a bug. The problem of the original system is a sudden drop in probability of the true alarm. It happens when the feedback of false alarm that is tightly coupled with the true alarm is given to the system. We call it false generalization problem. Literally, the problem is due to falsely generalizing the feedback from the user to suppress true alarm ranking. The figure describes the probability of nodes or random variables in the Bayesian network. Although computing the probability of every node is possible, we only show it for path 6, 7 in the top middle and the true alarm in the bottom right. Note that the true alarm 11 is marked with rather high probability 0.89. Suppose the false alarm 8 was the highest ranked alarm at the moment. Then, when the user says the alarm 8 is false, the alarm ranking system integrates the fact to recompute the probability of alarms. The computation is conditional inference over the Bayesian network. For example, see the bottom right of the figure. Before the feedback, the marginal probability of alarm 11 was 0.89. Then as the feedback is given, the probability of the alarm drops to 0.06. Basically, the system propagates the blame of misinforming the false alarm to the other facts in the graph. Those blame propagates to nodes that were involved in deriving that alarm 8 is highly likely a bug. The yellow nodes describe the blame propagating from the false alarm to the true alarm. The blame causes a drop in probability of the node. Then, the drop cascades to the tightly coupled true alarm as well. Eventually, the probability of a true alarm severely drops, causing false generalization problem. To mitigate such undesired impact, we try to add more facts that describes the provenance of the false alarm. For example, while deriving the fact that there is a path from line number 6 to 7, we find the loop is involved. Then, by adding the information, we checked the propagation of the blame is effectively mitigated. Now, even after the feedback to the false alarm is provided to the system, the probability of the true alarm drops by small amounts. To be specific, we focused on syntactic information since it can be easily generalized over programs. We can systematically automate the process of adding syntactic information according to the syntax of the programming language. It eventually improves the expressiveness of the probabilistic model compared to the original one that was only capable of expressing data flow. So this becomes the basic idea of our learning framework. Here's the overview of our suggested learning framework. The right-hand side of the pipeline shows the inference stage, which is already described in the previous slides. So let us focus on the learning part. First, we prepare a bug database. The database is a set of pairs of a program and its known bugs. From the database, we construct a probabilistic model per program using Bayesian network. Then, we simulate the user interactions with the alarm ranking system since we know which are bugs. From the simulation results, we spot the moment where the worst false generalization is happening. We can find the subnetwork that involves false and true alarms corresponding to the moment. From the network and the program, we try to add syntactic information that describes the false alarm. The candidate nodes for such addition are those contained in the shortest path from the false alarm to the common ancestor of alarms. For example, the nodes that are colored in green here. As shown before, we can systematically add the syntactic information according to the program and the language syntax. For example, the loop here. Then, we check if the just added information is actually good enough in mitigating the false generalization. The decision is made over the entire training set of programs. If half of the programs got improved, we accept the information. Otherwise, if it generally fails to give improvements over the programs, we reject it. We roll back the model to the previous step and proceed with the next worst moment of false generalization. We evaluated the learning framework with the following experiments. The benchmark consists of varying size of GNU software packages. We learned the model per analysis, where 11 programs for interval and 9 for taint analysis. For each program, we learned and validated the model according to the leave-on-out setting. That is, one program as a test set and the rest for the training set. Here's a result for the experiments. The benchmarks consists of programs that have much more alarms than the bugs. For example, in the interval analysis, there are 3 bugs among 700 alarms in average. For evaluation, we count the number of user interactions with the system until finding all the bugs. The baseline model, called bingo, reduces the number of alarms to be inspected by large amount. It is sufficient to inspect 75% less alarms to find bugs in a program for interval analysis. We can see that it already performs very well. Now here's the performance of our learning framework, indicated as red bars. With the learned models, we additionally improved by 33% for interval analysis and 22% for taint analysis. Furthermore, we evaluated our learning framework over the other alarm-making systems that use the same Bayesian network model. First, Drake integrates the information of code difference between versions. And DynaBoost integrates the dynamic analysis results. Here's the evaluation of learning applied to Drake and DynaBoost. Again, the baseline model already reduces the number of alarms to be inspected by a huge amount. In addition, both Drake and DynaBoost achieve much better performance. Then, here's the performance of our learning framework. With the learned models, we additionally improved by 54% for Drake and 20% for DynaBoost. In summary, we suggested and evaluated a learning framework for probabilistic models of static analysis alarms. The learned models achieve the outstanding performance by effectively mitigating the false generalizations. If you're interested, we highly recommend to read our paper. Thank you.